Hi there, this is Lucius Laframboise from ENG Suite, and today we're going to continue testing for normality by learning about the Jarque-Bera test. The Jarque-Bera goodness of fit test is another test used in engineering to determine if the data can be assumed to follow a normal distribution. And just like the Anderson-Darling and the Kolmogorov-Smirnov test, it's a hypothesis test, with the null hypothesis being that the data follow a normal distribution, and the alternative hypothesis being that the data do not follow a normal distribution, just like those other normality tests. But this one's a little bit different in how it works. The Jarque-Bera test compares the skewness and kurtosis of our data with the known skewness and kurtosis of the normal distribution. And then the JB test quantifies that excess skewness and excess kurtosis and combines those deviations into a single test statistic. So let's learn how those skewness and kurtosis get turned into a test statistic. It follows this relatively simple formula here, where JB equals n over 6 times s squared plus 1/4 times k minus 3 squared, where JB is our Jarque-Bera test statistic, n is the number of samples, s is the skewness of our data, and k is the kurtosis of our data. Now, if you remember, the whole purpose of the Jarque-Bera test is to calculate the excess skewness and excess kurtosis, and that's actually what this k minus 3 is. 3 is the known kurtosis of the normal distribution. So if we put in the skewness of the normal distribution, which is 0, you see that the skewness is being adjusted here, and so is the kurtosis. It's just because it's 0, we don't have to show that in the equation. Kind of cool. But something that we're going to want to do is, because of the way that we're going to be calculating our kurtosis, we're actually going to be calculating the excess kurtosis already. So we're going to substitute that k minus 3 with k sub e, being the excess kurtosis. So how do we calculate the skewness? Well, in softwares like ENG Sheets or Excel, it's incredibly easy. All we use is a function called skew, S-K-E-U, and then we plug in our data. But let's say you want to do it by yourself, or in the case of later in this video, we are going to calculate the skewness ourselves just to kind of see how that can happen. Well, one formula that you can use and that we're going to use later on is this one right here, where the skewness equals n times the sum of xi minus x bar cubed over n minus 1 times n minus 2 times the standard deviation cubed. And kurtosis gets a little bit harder, but it can be just as easy if you're in ENG Sheets or Excel, because all you have to do is use the curt function and pass in your data. But like I said, later in this video, we are going to calculate it all manually, because that's the point of this series, is to do it by hand, brute force. So the excess kurtosis, you'll notice, Ke, is returned by both of these. So the 3 is already subtracted from our kurtosis to give us the excess. The excess kurtosis formula that we're going to be using later on in this video is n plus 1 times n times the sum of xi minus x bar to the 4th over n minus 1 times n minus 2 times n minus 3 times the standard deviation to the 4th minus 3 times n minus 1 squared over n minus 2 times n minus 3, where n is the number of samples, xi is our ith sample, x bar is the sample mean, and sigma is our sample standard deviation. So we can put all of these together, and we have our formula for calculating the Jarque-Bera test statistic. But in order to use this to actually evaluate normality, we're going to want to turn this into a p-value again. So if the data come from a normal distribution, then the JB test statistic has a chi-squared distribution with 2 degrees of freedom. And this is really helpful because we can use the right-tailed chi-squared distribution with 2 degrees of freedom to calculate the p-value from the Jarque-Bera test statistic, because we're testing for the normal distribution. Which means in Excel and ENG Sheets, it's as simple as using a chi-sq.dis.rt of your JB and 2 degrees of freedom. But again, we're doing this brute force. So let's see what the formula we can use is. So the right-tailed p-value is going to be 1 minus the CDF p-value, 1 minus the left-tailed p-value. And something really cool is that the cumulative distribution function of the chi-squared distribution with 2 degrees of freedom follows this incredibly simple equation, 1 minus exp of minus x over 2. So again, CDF is our cumulative distribution function for the chi-squared distribution. X is the value we're going to evaluate the probability of, and df is our degrees of freedom. So if we plug in that CDF into our Jarque-Bera p-value equation, we see that p equals 1 minus, in parentheses, 1 minus exp of minus jb over 2. So if we distribute out that negative 1 and we add it all up, we find out that the 1's cancel each other out and that negative in front of exp also cancels out, which means that the p-value associated with the Jarque-Bera test statistic is p equals exp of negative jb over 2, an incredibly simple function. It's almost easier than actually using the chi-square.dist.rt because you have to type out more letters in order to do the chi-sq.dist. So kind of a cool, actually an incredibly cool simplification of calculating a p-value. So there's two methods again, the chi-squared.dist.rt and then exp of minus jb over 2. Both are incredibly easy. You get to pick, you'll get the same result either way. So interpreting the results is kind of similar to our others, where you can use your actual test statistic to gain some insight, but the p-value is really where you're going to be doing most of your evaluation. For the Jarque-Bera test statistic, higher values correspond to a lower probability that the data originated from a specified distribution. And if we look at our cumulative distribution function for the chi-squared distribution, we can totally see why. As our Jarque-Bera test statistic increases, so does our CDF. And since the value for the p-value is 1 minus our CDF, as the JB test statistic increases, the distance between our CDF and 1 becomes smaller and smaller. And as the JB test statistic goes down, that distance gets larger and larger, leading to a higher p-value. Now the p-value is just like all of our other p-values. We use a critical value to evaluate the p-value and determine if we fail to reject the null hypothesis or if we do reject the null hypothesis. Again, generally that critical value will be 0.05, but make sure to check with your organization so that you're using the right critical value. So let's take a look at a couple examples. Our first example here is our p-value equals 0.606531, and we have a critical value of 0.05. In this case, our p-value is greater than our critical, so we fail to reject the null hypothesis. The null hypothesis, again, is that the data follow a normal distribution. So if we fail to reject that, we fail to reject the data follow a normal distribution. Therefore, as engineers, we assume the data follow the normal distribution. Our next example, we'll use the same critical value of 0.05, but our p-value is going to be 0.049787. And even though that is so close to 0.05, it's still below 0.05. Therefore, we reject the null hypothesis. Reminder, the null hypothesis is that the data follow a normal distribution. Therefore, if we reject that assumption, we as engineers cannot assume that the data follow the normal distribution. So that's pretty much it for the math. It's pretty simple compared to our others, especially if you use built-in functions like skew and curt and chi-squared.dist.rt. But let's get a little bit complicated and let's do the math. Let's brute force it with all of those giant equations. All right, here we are in Excel, and I've already got this template set up for the Jarque-Bera test statistic and p-value. And if you want to use this template, go ahead into the link in the description. There will be a download link to this Excel file. It will have all of the math already done, but you can just delete that and follow along, or you can just put in your own data for it. So one thing that we're going to be doing here is we're going to first start over here and slowly work our way to calculating the JB and the p-value. One thing I like to do is sort my data. Now, for the Jarque-Bera test, you don't have to have it sorted. However, when summing, I generally like to have it sorted. I think it makes a little bit more sense if it doesn't matter. The first thing we're going to do is we are going to take the difference between each value and our mean. I already have the mean calculated here, and then I'm going to F4 to absolute reference that. Then I can just double click and automatically fill down. The next thing we're going to do is we're going to cube each of those differences. And we're going to the third, we use the power function. And then again, double click to drop it down. This time we will again use the power function to raise that xi minus x bar to the fourth. Enter. Double click to drop down. Okay, that was pretty easy. Now we're going to get a little bit more complicated because we're actually going to take a look at skewness and kurtosis. So the first thing we're going to calculate is the skewness because it's a little bit easier. And I have it split up into a numerator and denominator to keep things a little bit easier. And I'm just going to start by dividing those. So skewness equals numerator divided by denominator. And the numerator equals n times the sum of our xi minus x bar cubed. And I want to make sure I start with the first value. Enter. Wonderful. Now our denominator equals n minus 1 times n minus 2 times, and then this one here, we're going to take our standard deviation and cube it, so we'll use the power function. Select our standard deviation and cube that. Awesome, we have our skewness. Let's just double check and see what we get when we compare it to the built-in XL function. Excellent, excellent. All right, I'm just going to get rid of that to make things cleaner. And now we're ready to move on to kurtosis. So kurtosis, I've split it up into an A and a B, and then A numerator, A denominator, B numerator, B denominator. So the first thing we'll do is we will take A, minus B. Enter. And the first one we're going to work on is A. It's a little bit more complicated, so it'll feel really good once we're done with this. And that's A numerator divided by A denominator. All right, so the A numerator equals, and in parentheses, we're going to put n plus 1 times n times the sum of our xi minus x bar to the fourth column. Enter. All right, and now our denominator for A is n minus 1 times n minus 2 times n minus 3 times, and we'll do power, standard deviation to the fourth. All right, awesome. So there we have our A calculated, and B's a little bit easier. It's just the numerator here is 3 times n minus 1, but we have to square that. So I'm going to put this into the power function and square it. B denominator equals, and we're going to do n minus 2 times n minus 3. Then we take our B numerator divided by B denominator and enter. And there we have a kurtosis value. Let's check it against the built-in kurt function. Enter. Perfect. We get the same value. Awesome. So now we can use our Jarque-Bera Test statistic formula, which equals, and I'm going to just put this in parentheses, n divided by 6 times, and then everything in here is going to be in parentheses. We are going to say power skewness squared, and then plus 0.25 times, again, power, our excess kurtosis squared. Enter. There's our Jarque-Bera. Now we're going to plug it in to our associated p-value here, which is a very simple function, equals exp of negative jb over 2. Awesome. Now let's test it against QE Suite and see if we got the correct results. Do that. And then hide our graph. And there we go. We did the Jarque-Bera test. Incredibly simple, and we can even get simpler if we were to use our skewness and kurt functions along with the built-in chi-squared dist. Thank you so much for watching. Have a great day, and please do something awesome.